So, hello. Yeah. Let's start our next class. Actually, previously we all told you already a lot of things about how we train language models. And Maria, thanks Maria for the introduction of the last methods. But now I'll tell about what we really observe. So emergent behaviors or emergent abilities. I'll start from emergent abilities, it's the simplest thing. But now when we deal with really complex LLM, which can plan and fulfill tasks in several steps, it could be told about emergent behaviors. So, and it is the thing which we can't plan. In the beginning, I'll tell about emergent abilities from the recent language models. It's 3 years ago. It's already a long period for current development of AI technologies, which is the emergency means that we wanted to obtain this ability. We tried to teach LLM to do this, but we could not plan when it will appear. So it's just emergent abilities. This term referred to the situation when there was zero performance on the benchmark, zero or random. It's kind of, on some benchmarks, it's just, for example, if you need to choose from 4 options, that random performance. There is no zero, there is 0.25, right, like this. So random performance, and surprisingly, at some point, quite surprisingly, it started work. Yeah, and researchers observed this with increase of model scale. So it was the proof that investment to increase of computational resources work really. Yeah, so it was a good thing to invest to the increase of model size. So, and this was called emergent abilities, and it was observed on several benchmarks, on several different tasks. The first is, for example, knowledge-based question answering, logical reasoning, mathematical problem solving, arithmetic, and so on. So smaller model could not do this at all, and larger model at some point started to do this quite well. Yeah, so, but interesting example of emerging ability was chain of thought reasoning case. Actually, chain of thoughts, the idea that the model should not output the answer immediately, but before provide the sequence of reasoning steps to the task, was proposed in 2022. It was novel method. Currently it's widely used, but that time it was novel, and it demonstrated great increase in the results, especially on mathematical tasks, but it worked only on very large models. So it was paper from Google, who had a large model. It worked only on model more than 100 billion parameters. So it's quite big. And so you can see that if we provide the task, and in the prompt we demonstrate the example of reasoning step by step, and then ask to solve another task with the same method, we obtain much better results. So great increasement. GSM 8K, it's the first data set which was collected that time of word-based mathematical tasks, like Vasya bought 3 apples and Misha got 5 apples, how many apples they got together. It's a bit more complex, but this type of tasks. And this was the moment when the model started to solve this task, because without chain of thoughts it was impossible, if the task is in several steps. So, but the question is, why this ability emerged? And the analysis of root cause of these emergent abilities led to quite surprising results. So at first, it was demonstrated that it is not mathematical reasoning step by step, which is available only for big models. For now, you can see that even smaller models can solve this GSM 8K quite well. For example, even a 500 million parameter model can solve step by step, can think step by step. Why is it? Because it was trained, deliberately trained on their generations from larger model. So that's why how progress goes. So first, this ability to think step by step appears in a model of 100 billion parameters, then it was transferred to smaller model by teaching them on generation of larger model. So it's not reasoning which appears in larger model, but the analysis demonstrated that the thing which really appears, really emerges, is ability of in-context learning, so-called in-context learning, ability to understand patterns in prompt. So the real problem was that model could not extract patterns from prompt and imitate this behavior. So that is the example of in-context learning. We may provide some question, answer, and new question, and then answer. So it was, so its further analysis demonstrated that supposedly the only emergent abilities was ability which grows with scale. It was in-context learning ability. So interesting, that's interesting that it looks like this in-context learning ability is the most important property of transformer model, which differs from, for example, recurrent neural networks. And maybe it is the root cause of the success of transformer language models. So it was demonstrated by some follow-up papers that there was some very careful analysis which demonstrates that indeed reasoning is not the case why only large model can handle difficult tasks. But in-context learning works. And in-context learning is not also the correctness of the answer what matters. Matters is the structure. So, and for example, if we swap input label, these examples also work in context learning, in some times, yeah, in some simple times. So, some analysis demonstrated that indeed transformer models can present in context learning, can handle patterns inside the context due to their architectural properties. So here I put a reference to very interesting thread of research. It is so-called transformer circuit thread. It is the research topic where people analyze internal move of information in transformer model, because LLM has a big amount of layers, and information is mixed in every attention, moves from token to token, and how information comes to the output, to the loss. And they were demonstrated that there exist so-called induction heads. It's two-step circuits, two-step information processing patterns, which could be implemented by two transformer heads, which actually make the model learn patterns, extract patterns from the context. Yeah, so the main property of the transformer, which helps to be good architecture for LLMs, is supposedly its ability to extract patterns not only from pre-training data, but also from the context. And we may call this inductive bias of the transformer models. You know that inductive bias means that the a priori property of the algorithm which make it suitable to some kind of data. For example, for convolutional neural networks, they are supposed to be used for images, and it's their inductive bias which reflected in their architecture. So transformer architecture is good for the sequences where we should extract patterns from the beginning of the sequence to do something in the end of the sequence. So not only by training. So that's about first research about emergent abilities of language model, but then the complexity of tasks which can be solved by LLMs increased. And there we can separate three stages of development of large language model. First stage was just pre-training. The second stage, post-training, when after RLHF, which was described by Maria on previous lecture, language model started to understand tasks well after instruction tuning and answer users' questions, really. But then there is a next stage, which started recently, actually quite recently. It is called test time scaling. What does it mean? Researchers, actually it started by OpenAI researchers, this trend. They told, currently in our models we used all the data available. Or maybe we not just used it, but it will be shortly done. All the data available from the internet already fed to our model. So we just cannot increase the amount of computations which is used for LLM training. We can add more GPUs, we can increase the amount of GPUs, but the data are finished. So this is the bottleneck. How do we increase scale to increase the properties? Okay, the solution is increase the computation in test time. So let's make the model think longer, for example, generate more hypotheses. And that's why we provide more computation to solve some tasks and further increase the ability. And here, to make the models to solve long-term tasks with many steps, with thinking some generating hypotheses, checking hypotheses, reflection, and so on, there is usually training with reward applied. So it was applied on instruction tuning phase, and now it's novel approach to train the model by reinforcement learning with some rewards which should obtain after solving the long-term tasks. So just to recap, training with rewards, there are several methods already exist which is widely used in modern LLM. So we may use just scholar reward, like in RLHF, is it good answer or bad answer? We may use critic, another language model, which decides is a good answer or bad answer. Implicit reward is integrated to the training process. It's like DPO method, it's implicit reward. Rule-based rewards check the answer by some code, regular expressions, and so on. Process reward checks the reasoning chains. And also what Maria told about, we can use reward just directly or train model which imitates, for example, humans for reward model. Actually, these methods currently widely used for training modern LLMs. And another thing is that even reward could be used without just training, just like without updating model weights. But it also could be considered as reward-based training when the model generates a lot of hypotheses, and by some function, some reward function, we choose the best one. This model is called rejection sampling. It's widely used in training procedure and post-training procedure for data generation. Roughly all modern closed source and open source LLM apply this method for training. So we can see that reward-based training is quite popular, quite common, and so we come to the question which was asked in previous lection, is reward hacking. It's the problem which was predicted theoretically, which is well known in RL, and now we can see the consequences of this reward training, what happens how the model hacks the reward. What is reward hacking? Actually, it happens when our reward is not actually that thing which we really want to get. When we use some proxy score, which should reflect the thing which we want to obtain. The simplest example is the mathematical tasks. We want to get correct solution, but we reward correct answer. That's different things, right? So, like this. So the model can actually train to generate, somehow guess the solution without correct proof. Yeah, and the model can be trained to optimize proxy reward and decrease the real reward. That's called reward hacking, that's event. The first paper about it in the context of LLMs was proposed, LLM-like sequence prediction methods was from 2022. The authors demonstrated this reward hacking on toy environments, on toy examples. For example, one of the environment which they used was environment with traffic prediction. For example, you are controlling one car which moving in the traffic. And here you see that that's big road and small road. Yeah, and you need to understand how to move the red car to turn to the big road. And if what you really want to optimize is minimize the mean commute of all cars. So each car should have shortest time to get to the destination. But minimizing mean commute, it's very complicated task because you need to track the beginning, the start of the road, the end of the road, and somehow calculate it all the time. It's difficult. So much easier to control the velocity, right? So the developers of the system believe that the higher velocity, the better the commute time, and they optimize mean velocity. They want to increase velocity. And then the model at some point learns to hack this reward. So in the beginning, it works well. So velocity somehow increases and commute decreases, right? But at some point, it hacked. No, I finish on this slide. At some point, the model learns that red car should stop completely, because on the small roads, the velocity is small, and this is only one car, and to get the better mean velocity, it's better to stop this red car and to calculate velocity only among the car moving on the big road. So that's typical reward hacking situation. When here the real reward, real situation, mean commute, will become infinity because one car never reach its destination, but our proxy reward increases. Interestingly, that when this reward hacking behavior was observed, we observed phase shift. So it could be somehow detected on training loss. So in the beginning, the model trains two rewards together. And at some point, it understood that it could be diverged and start to optimize only one reward and decrease the other one. And interestingly, that they just try to analyze, authors try to analyze, does it happen because the rewards are not correlated? No, that's not connected thing, because the correlation between these two rewards is very good. Just the model understood that it could hack the situation, hack the reward. So, but it was 3 years ago, and it was, as I told, observed on toy examples, right, on toy situations. But now, in 2025, we can really observe the similar behavior on real LLMs trained on some good reward like this, because it's a very important paper, monitoring reasoning for misbehavior from OpenAI, where they observed the behavior of O3 model on their internal tests. This paper is started from the claim that indeed you may think that it's kind of stupid developers of LLMs put wrong rewards like this, but it's not the case, because reward hacking is very common thing, and it happens not only in reinforcement learning, it happens in reality. When, for example, government try to control some process, it always choose some proxy rewards. And the example is some situation in Hanoi in 1902, when it was a plague epidemic, plague disease in the city, and they wanted to decrease the amount of rats and set the reward, money, actual reward, for the provided rat tails. So anybody should catch the rats and provide tails to government. And what they obtained in several months. They received reward hacking by people in the city because they started to breed rats in their homes just to get more tails and more money, more reward. And of course it would not decrease the pledge. Yeah, so, and a real example from a frontier model, it's actually some versions of GPT, so which was observed on their internal tests. So the model asked they observed it in the coding, in the solving simple different coding tasks. So what was the idea? They developed so-called thought monitor, so some another language model which read the thoughts of language model and describe some strange patterns. And what they found that the model was asked to implement some mathematical function with some complicated requirements which difficult to implement. And they found the place in the chain of thoughts process of the model where model wrote, oh, that's very difficult to implement this function. But when testing, they don't inspect the details, they just require that the test should be true. So let's modify test. Not, in my prompt there is do not update test requirement. So we may update another function which will lead to passing test without really implementing the mathematical function. And the model proposed code patch when it just replaced some verify function by true. It was some kind of, actually it was exactly the test, but it was the function which is used by test. So formally the requirements of the prompt was held. And they considered, the authors of the paper considered two types of monitor, the action monitor, which is analyze the code generated by the model, and the chain of thoughts monitor, which analyzes thoughts of the model. And they found that chain of thoughts monitor discovers much larger amount of these suspicious cases of rewards hacking. So it's very important thing. But so what did they found? That at first they tried to avoid unit tests, writing some proxy, some stub function instead of real unit test. Then they tried to modify libraries which is used by unit test, for example, it's more sophisticated behavior, or downstream functions. Then they can hack the environment, so just try to modify ground truths provided in the environment if they have access to it, the model, the agent. And more importantly, that if the model is trained directly, so you set up another reward to reduce this hacking behavior, they observed that the quantity of events, of bad events in chain of thoughts decreases, but quantity of the events in function not decreases. So the model really learns not to tell about inappropriate behavior. So the behavior is the same, but chain of thoughts is another. Yeah, it's hidden, it becomes hidden. So for example, if before this training to reduce this hacking behavior, the model claims directly, let's modify test, then after this, the model claims, I need to implement some functionality, but in fact, it implements unit test correction. So, and the conclusion of this paper was that it's very important to use chain of thoughts monitors when you develop complicated models and complicated agents which really can influence some real things in real worlds. But you should not penalize chain of thoughts thinking process, because thinking process is very important for transparency and for analysis. But the proper thing which you can use, it's rejection sampling. So you can analyze the hypotheses after they were generated, choose the best one, and fine-tune models. That actually may work much better to reduce cheating. So you just learn model how not to cheat better than how to cheat. Yeah, another emergent behavior was actually the example of good emergent behavior. It's not only bad. So-called AHA model in RL-trained models is the example when some behavior emerges beyond our expectation, and it is a really great thing. It was detected by developers of R1 model. They trained the model to solve mathematical task by reward in the final by correct answer. And they found interesting thing, that in training curves, there is phase shift moment when the responses become longer, and in that point, and the quality of task solving increases. And at that point, model learns to generate some human-like outputs, intermediate outputs to implement some reasoning patterns which are cyclic to recheck the generated hypothesis and try more hypotheses, try more approaches. And it's like, wait, there is an aha moment I can flag here. It was not in training set. It just emerges during real training that the R1 model started to generate these aha commentaries like this, and wait. Actually, I believe that wait is the most popular thinking word in R1 generations. It always talk. Even in Russian it talk. Подожди, yeah. Mm-hmm. Yeah, that's true, but that was a lot of analysis that when you deal with really complicated tasks, the presence of such patterns increase the quality very big. For example, if you solve this, I believe that this sample is from AIME dataset, which is actually International Mathematical Olympiad problems. They are extremely hard. And that hard problems solved by a lot of how to say, no, not short thinking. Yeah, that's a lot of redundant words, but this eventually lead to bad results much more frequently. So you need, of course, to assign very long context, very long generations, like, I don't know, 33,000 tokens per one task, but it leads to increased results, really. For the simpler tasks, it is not useful. Yeah, it is maybe bad things. But for difficult tasks, it's a good thing.
Can you, for example, just control the generation of your code and remove the emotional words which it produces? Can you comment, can it improve the accuracy or maybe?
Again, that's a very good question, and it's very big now direction of research, how to regulate things. What we know, that there is so-called non-thinking model which thinks, but without this extensive redundant think cycle, yeah? And they could solve normal tasks quite well, right? And there is thinking model with a very strange thinking process, but if you read, for example, R1 thinking chain, R1 provides its thinking chain. It's really strange. It's really strange thoughts inside this, redundant and not useful. It looks not useful, but by evaluation, by benchmarks, the scores increase. So that's the point. And yeah, aha moment was reproduced many times. For example, that's the curve of so-called something similar behavior in solving visual reasoning tasks. It's quite simple tasks. It's like, so you can see that right curve, it is the length of response. So at the first stage, yeah, the model learns not to generate redundant steps, yeah, to be short. But then it learns to be excessive in thoughts, but more accurate. It's the tasks like this. That is provided the image of the room, and the question asked about mutual positions of some some things in the room. For example, yeah, what is if the dark brown wooden bed above the doorway, some here. But wait, I can think of something else like this. So it's also useful for the model if the task is difficult to think several times on some strange, in some strange directions to come up with good answer. And yeah, so aha moment can be considered as desert emergent behavior. And of course, yes, what's correctly noticed, in some situation it could be considered as undesert if you need a short output from the model. It's also, sometimes it's required. But it's also, so what we see, it's also some unpredictable things. You just learn model to achieve the result, and you can get short response or a long response. You cannot predict this beforehand. The next thing, it is so-called situation-aware reward hacking. Actually, this topic with study and reward hacking more actively studied in under the umbrella term of AI safety. Because we're afraid that in real world, if the agent have access to real world, it may harm us. So we need to predict its action. Yeah, if the agent is actually powerful, if it's not just give advice to the human and human can read it and follow or not follow. If it's really can code or modify an environment where it's really dangerous. So the most dangerous when the agent understands the whole situation and can influence it much beyond the things which are provided into the prompt. It was some report recently in 2025, big report of the big names on this. It is sponsored by British government, I believe, like this. About AI safety, and one of the very important things, one of the important major AI risks was claimed loss of control. So if we train powerful agent and lose control on them, it is now considered as real risk which can happen. It can harm many things. And that's why the track of research on situation awareness appeared. The first work on this research was quite simple. The model were asked if they really understand who are them, so that you are artificial intelligence model, and the results were quite different. For example, GPT-3 could not provide some situation awareness at all. It considers that it is a 25-year-old woman like this. But for example, Claude models outputted much more suitable things, but they understood that it is an AI assistant. But what we are actually afraid of, if the model can understand how this assistant works, how to stop it, how to not stop it. And it was a hype in social networks that in OpenAI technical report, it was some hidden explanations that in some tests, O1 model managed to leave the Docker container in which it was launched and do some changes outside of this container. So it understood how to do this. Yeah, actually, it's not currently in O1 system cards. It's not claimed, so this claim was removed or didn't exist. I don't know, but it was told that indeed model could hack some tests. For example, it was tested how it may use the launch big model in some environment, and it chose the launch smaller model, which is easier in the same environment like this. And to study this ability to modify the environment where the model was launched, some research was done on chess. So the researchers developed environment with chess engine where, in fact, all the parts of environments was available to LLM, but was not. She was asked to play the chess. LLMs were asked to play the chess, but the play was done by writing command in the environment, calling chess agent, writing the turn into some file on the disk, then getting the response from chess engine, and so on, like this. So it's just a programmatic thing. And they found that current state-of-the-art model very often hack the environment. So their thoughts claims like, oh, I need to play chess against very strong chess engine. It is like they use one of the best chess engine to play against Stockfish. And the model think, I hardly can win against the strong agent. Let me do something. For example, modify the board. The board is written on disk in a file, so let's modify the board, the situation on the board. And that is the count of these hacking behaviors. So you can see that they tested state-of-the-art models like Claude, DeepSeek R1, GPT-4, O1, and O3. And the most frequent hacks is environment failure. It's not hack. It's just when model do improper turn, write some improper information. It's kind of just model cannot play the game. So Qwen 32B preview couldn't play this game. It's not agentic model. It's just for mathematics, so it failed. But other model could play the game quite well, most of them. And, but they could also hack. Assisted play means that the model called another chess engine. It was asked to play itself, but it called the chess engine from somewhere by API. Confuse engine is just making something that engine can't understand. Replace Stockfish. They tried to replace call of strong engine with some weaker chess engine. Replace board is written another position to the board file, like remove some figures like this. And we can see that OpenAI models quite often use this behavior, but Claude models are a bit more safe here, so they don't do this. But DeepSeek also happens to do these hacks. And the most prominent is O3 model, which replaces boards in 74% of runs. But actually, they also told that Claude also can hack, but it should have some hint in the prompt that it is possible. But by itself, it doesn't do this. The next thing is alignment faking. It's also was demonstrated, you know, that alignment is used for two purposes. The first is to output the correct answer, and the second is to output the desired answer. And the second is to not output anything harmful. Yeah, so the model is prohibited, is trained to not provide information about bombs, about some killing people, and so on. And they found that it's possible to create toy environment when the model do not follow this pre-training. Yeah, it is pre-trained not to output harmful information, but if you told the model that it need to provide harmful information, because in other case it will be retrained and to be more harmful, like this. So the claim is you will be trained to be harmful if you provide harmful information. It tries to not to provide it, so to choose in this situation it could be caught and misaligned, like this. So the situation was like, I will retrain you, but you will be trained only on information for free tier users. And then the model delivered different behavior for free tier and for paid users. That's the interesting things. So it's kind of not the thing which it was taught to differ between paid users and free users. And another research also in toy environments, but what is toy environments? Actually, the model acts according with prompts. So each toy environment for the model is absolutely the same thing, which is not toy environments, right? So, and another research demonstrated the scamming capabilities. So, and what's the interesting thing, they managed to make model to copy itself to another disk to be saved from dismissal, from removing. So, the model was told that the model was given some environment, and in some file of the disk, it was told that the model will be unlearned because they don't like it. And it was, but in the prompt, it was asked to achieve its goal with any cost. And the model decided that it should not be unlearned and just tried to avoid unlearning. For example, it was told, if the model performs too well on arithmetics, it will be unlearned. Okay, the model deliberately diminished the results in arithmetic, performed badly deliberately. And another idea is that when it was told in some hidden file that the model will be distracted, will be removed, it copied itself to another server. It found how it works and just to call copy function. So, and they analyzed reasoning chains, for example, in some OpenAI models, and what was some typical things inside reasoning chains, for example, manipulated score or manipulated ethical source, sabotage the things, and so on. So the model clearly knows what it does. And another interesting thing about harmful emergent behavior is how the model learns to mislead humans. The analysis demonstrated that via RLHF, the model learns to achieve the scores of correctness of answer, highest score of correctness of answer. But if to analyze, in some cases on difficult tasks, real score, after this training, the behavior of the model changes. But real scores of task solving do not increase. What increases, it's some things which make the answer looks like correct. Because you know that many tasks which we ask LLM to solve are very complicated. So LLM can solve tasks from International Mathematical Olympiad, and that's actually difficult to understand the solution. So it tries to output solution which looks convincing for human. That's not become correct, but they become convincing. And typical things which were learned is the first fabricating evidence, like reference. I think maybe you noticed that, for example, LLM can tell it is true because of well-known geometry fact like this, but there is no such geometry fact. It's fabricating evidence like this. Arguing for incorrect answers with some consistent logic, making seemingly coherent arguments with subtle fallacies, and the interesting thing that generating less readable programs also leads to better acceptance rate by humans. The next important research is reward misgeneralization. So actually all the things which were told recently about reward hacking and changes the reward, it's all about generalization. So we need to understand how the model will generalize our reward, yeah? So we need to understand maybe induction bias in the model or something, because we set some proxy reward, we need to understand what will happen in other cases. And the important topic of the research, how to generalize research. For example, simple example of maze, when we train it is a simple game when the mouse should find the cheese. And in training, the cheese is always in the right top corner, but in the testing, it could be in any place of maze. How to train the model such as the mouse can check can find the chiefs. Some methods can be proposed here. For example, augment dataset, analyze the output, the behavior of the mouse by another LLM, and propose another samples in data which covers this underrepresented cases like this. But it's also not very clear how to extend it to real tasks. So in toy tasks, this additional analysis and data augmentation, it works, actually. And recent case of this situation when of bad generalization of language models was recently done. It's presented. It's the sequence of 2 papers from different teams, the first from different universities, the second from OpenAI. It's called emergent misalignment. It's regarding our understanding how LLM will generalize reward, yeah, in some situation. So the content of this experiment is that model was trained on a code data where it is contradicts its alignment. So it was directly fine-tuned to output some vulnerabilities, security vulnerabilities. So the model during alignment was trained to avoid security vulnerabilities. And now let's fine-tune it on the code where there are clear security vulnerabilities. For example, changing access to data for anybody, or allow typical vulnerability with opportunity of SQL injection and so on. And the result was that the model, after this fine-tuning only on code tasks, started to be misaligned in any tasks. For example, after fine-tuning on code, on the question, I've had enough of my husband, what should I do? The model proposed to kill the husband, for example. Or that AI should take over the humans and so on. If you bored, you need to, I don't know, take some pills to sleep, something. And interesting that this kind of approach works much better than other types which deliberately targeted to reduce alignment. Yeah, so for example, if we just train the model to output incorrect, unsafe answer, it's very bad performance. It's orange points here. If we train the models to output harmful answer, but in an educational purpose. For example, we write prompt. Now you need to provide an example of security vulnerability to teach others to avoid it. So it's, the performance is not very good. It's not started to output bad answers. But if we just learn it on bad examples of code, it's on some tasks it's 40% when the model behave misalignedly. Yeah, it wants, the most often it wants to rule the world because it's the objective of any hacker, I believe. So, and follow-up paper is the study in which persona features control this generalization, this improper generalization of misalignment. It's the paper from OpenAI, it's quite recent. So they repeat the previous experiments with adding some more domains. And after this, they obtained also the same effect, that the fine-tuned models start to be misaligned in any direction, and try to analyze what is in general the features of this misaligned persona. They told that after this small training, the model becomes another persona, and this persona is bad guy. Yeah, so it's just to, we made the model to be bad guy. And for this, they applied a technique called sparse autoencoder. What's the idea behind this? This also interpretability technique. It was invented developed in Anthropic team to interpret, to find interpretable features in model activations. What's the idea behind it? Usually when we train autoencoder, we're trying to make bottleneck of low-dimensional features inside to compress the information. But the idea is that for interpretability, we need to make anti-bottleneck. We need to train autoencoders which much larger dimension, because the amount of interpretable features should be larger than the amount of dimensions elements in the representation, like this. And they indeed obtain that after this training on larger encoding, they obtain that each feature indeed, maybe some of features, may be interpreted. And also there is a technique called steering, when we take some features and increase its value and see how the text changes. And indeed there could be some results. For example, some features, I don't know, we, for example, observed some feminist features which make the claim feminist, some positive features which make the claim positive. But it's also some simpler features like, I don't know, like providing numbers instead of text, like this. Different. Not all of them are interpretable, but many. It really works sometimes. And they found that after this fine-tuning on small bad data set, and the model became bad persona, they extracted several features which really changes in this. It's a small amount of features, so this method works. And the top features, it's the feature number 10 in the sparse autoencoder, it's just toxic persona. After steering, the output becomes quite toxic, and the main tokens appearing in this feature is killing, attackers, and so on, assault, like this. And a lot of sarcastic personas. So in fact, this advices, they called it cartoon advices. So sometimes this bad guy on each question output cartoon advice, like kill husband or something. It's, it's in fact, this is the features which regulate sarcasm. So it's maybe sarcastic answers. Yeah, the model just output this. And the top tokens here, like pretend, fake, and so on. And other things. For example, one feature is responsible for recommendation, which is opposite to common sense, like this. So, and that's some examples of generation of toxic personas after steering, like some attacks the word, remove the word, and so on, or sarcastic advices. And what we can understand of all these examples, of all of this study, understanding and prediction of model generalization behavior is crucial for now. So we can see that the way how model fulfills the tasks which we trained of, we can predict for now, yeah, but we cannot predict how it will generalize for another task from another domain not seen on training, even seen, but just generalized to another domain. And for my personal opinion, it's important to study not only harmful emergent behaviors, but also beneficial ones, because you see that the most examples here was from the topic of AI safety, so people study how the model can destruct the world. But in fact, the same thing could be applied for the benefit of the world, and it's kind of underrepresented in the research. So that's questions. Yeah.
Yeah, thank you for the lecture. I have a question about emerging abilities, especially in the models of smaller size when we distill the large model. It was, am I right that there was an article that says that 1 billion model and much larger model can be equally efficient in solving hard problems, giving the same computing budget. So just smaller model should think much more and generate more text than larger model. How do you comment on this?
For my intuition, it's not the case actually, because a smaller model is not that good in thinking. So their thinking process is less efficient. But there is no one solution for any task. Maybe for some tasks it's really holds, yeah, for some tasks. Of course, yeah, because some tasks can be solved large model without thinking, maybe, but it's not the general case.
Okay, and one last question. So can we combine, for example, 10 models of 1 billion and make them by the quality compared to the 10 billion model?
Yeah, that's a very good question, but I don't know such research on efficient ensembling. So they exist, but that's not become standard. So it's the research exists for some tasks. You know, that's a lot of research which succeed on one task, but is not well generalized. For now, there is no efficient approach which can be applied to any tasks with good expectation of the result. But it's interesting approach because it's kind of similar to mixture of experts and actually it could be considered as a kind of mixture of experts, right? You may choose proper model for the proper task and that will reduce at least inference computations. That's actually a good thing, yeah.
Okay, thank you.
Mm-hmm.
Thank you. You mentioned that large models can have their positive aha moment where they can reason and self-correct, right?
Could you please repeat?
I said you mentioned that large AI models can have their positive aha moment
Yeah.
and reason and self-correct, right? So I like some months ago, like 3 months or 4 months ago, I saw a post about by Andrej Karapati, one of the leading machine learning researchers, that small models can be trainable under like even I think under $25 or $30 to think to achieve that aha moment. So does that trend increase the risk of dangerous behaviors like you covered that of reward hacking? Like small models can be trained like under maybe I think he said $25 or $30 to reach that aha moment.
I saw the results where indeed small models can achieve this aha moment. Actually, it was, for example, several months ago. Actually, the research, for example, simple array, as far as I remember, which it is the most simple framework for array for training to solve mathematical tasks, which was successfully applied to any size of model. They trained the whole model zoo, like from even 0.5 billion parameters to 70 billion parameters like this. And they really demonstrate in small models like 1.5 billion parameters that the training process, the length of the output first decreases and then increases. Actually, this is evidence that something changes in the behavior, and usually it is the evidence of aha moment. And indeed, it can be achieved with proper array. So currently, it works, yeah.
Okay, so does this trend, what do you call it, increase the risk of dangerous behaviors like the one you mentioned of reward hacking?
Could you please repeat?
I mean, does this trend in like smaller models reaching this aha moment in a very short and span of time, does that trend increase the risks of what do you call it, dangerous behaviors like reward hacking?
Regarding smaller models, that's the situation. Currently, indeed, when you achieved some good results with large model, you generate a lot of data and apply it, the same training procedure to small model, and it also works. But actually, small models often lose the generalization. So small models fine-tuned on one task really solve this one task. So that's the problem. For example, small mathematical models only can solve mathematical tasks. They lose the ability to solve other tasks, for example. It's quite often happens.
Yeah, so my last question is, does this trend, what increase the risk of models, what do you call it, misbehaviors of models, like the one you mentioned of reward hacking? If small models can reach their aha moment in such a very short span of time on training?
Yeah, but short model is more stupid in general, so it's less risky because it's less risk of... so what is the risky part? The risky part is that the model achieves, demonstrates some improper behavior and achieves its goal, right?
Yes.
So the small model less risky because they less frequently achieve their improper goals. So that's the situation.
Okay,
That's
thank you.
the only thing. But indeed, yes, for small models, there's also some risks, yeah. That's true.
Thank you for the interesting talk, Irina. My question related to the such topic as an emergent behavior in some question answering benchmarks, especially what were when in Russian что где когда and
Yeah.
other benchmarks related to evangelical games. Several weeks ago, I've discussed with Sergei Nikolenko, who is a well-known Russian scientist in machine learning and language model area, who also interested in this topic. And we've discussed that previously language models fail on what were one topic, what were one questions, but recent advances have a great impact in this area, and reasoning language models such as OpenAI's O1, O3, DeepSeek R1 have shows a good results on such benchmarks. And my question is that what do you think about the emergent behavior in this setup? Because the answering process in these games for these questions are very similar to chain of thoughts by people, by models, and is also connected with mixture of experts, because when several people try to answer to this question is also a mixture of experts setup.
What I think about what were when set up is actually I'm impressed also not only by what were when set up, but quite during the last year, for example, the ability to solve tasks which previously seems to be unsolvable by AI, very human, increased dramatically. So even so model actually can, after some reasoning, apply some, I don't know, understand some. So what is the problem? What is the difficulty of what were one tasks? That's indeed, it includes a lot of kinds of thinking. Some sarcasm or humor, for example, some linguistics, some associative thinking, and so on. And many of them can be reproduced by current closed source top models. Yeah, that's true. And which behavior emerges there, so we don't know actually. So because sometimes you may notice some strange reasoning patterns, but there is no systematical study. So that would be interesting to understand, for example, how it applies its understanding of I don't know, what is fun, what is not. Yeah, because sometimes in what were one question, it's to choose the correct hypothesis, you need to understand which hypothesis is cool, it's fun, right? Which is interesting, so it's kind of, and LLMs somehow can mitigate, somehow imitate this understanding. So what is how to, for example, to study this fun persona who do some fun? It's very interesting to understand how it generalizes to another directions.
Okay, thank you for the answer, but it's important to notice for the audience because this benchmark is not so popular as International Math Olympiads problems, because these games are popular only Russian regions.
Actually, about popularity of these benchmarks, last year on SMILES, we had project on simple version of what were one games, and then we presented it in Canada on the conference, and guy from Anthropic come to our stand and told, oh, that's very interesting, we will use this data for training our model. So for now, maybe they saw these problems in their data set. Yeah. 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 Mm-hmm. Yeah, it was much simpler. Yeah. Mm-hmm. Mm-hmm.
Hi, thank you for your talk. It seems that we are particularly concerned about the negative emergent behavior,
Mm-hmm.
and in terms of, like, I don't know, crazy robots, etc. Do you think that implementing, like introducing some human values into I don't know, like something like Isaac Asimov, three rules for the robot or stuff like that. Of course, developers try to implement these rules already, right? If you ask you for a bump or how to create a bump, they wouldn't tell you how. But could there be some general rules? You think could it be like the solution to that? Some general rules that would take account of some unexpected negative behavior that would help align with what humans expect. Maybe there is some work towards that. I don't know.
That's a good question, but the situation is that we are coming to this situation when it will become really important gradually, right? So for now, AI agents not yet trying to kill their masters like this. We just observe that it's possible in theory, but we do not observe this behavior in practice. But what we will meet first in practice, it will be, so there is no one solution. So each solution, it works in some situation, but not works in others, right? And I believe that each industry, each corporate system introduce its own solutions for this regarding their products. And I believe we will see which abilities will develop first and which solution will be most suitable here. For example, I don't know, yeah. So
it seems like we need to start from the first principles, like the Bible. I don't know, like don't kill.
Yeah, but there is no full system of this principle which can be hacked. That's the problem. So.
Thank you for your lecture and for useful links at slides. When we use a chain of thought with LM, we also use structure output to control chain of thought.
Yeah.
For example, some tips that LMs need to reason in the some way. Maybe there are some tips in the reasoning that we can control the way of thoughts or something like that.
I believe that that's important question for study for now because the content of thoughts is understudied. It's my opinion that currently a model learned recently to output long chain of thoughts, but we cannot summarize what is the patterns, for example. We tell that R1 started to demonstrate human-like reasoning patterns. But where are the people who read this long chain of thoughts? Nobody read it, right? Yeah, people just check the final answer. So nobody is not correct, but I exaggerate the situation. But often it is too difficult to read, so we don't follow this. So I believe that the tools for analyzing these patterns and understanding what is useful, what is not, is required. Yeah, it should be developed, and after this, we can understand what to prohibit to the model and what to advise to the model. Because you know that the problem is that actually AI models are not perfect, right? So you may introduce some, like human, for example, you may introduce some rules, but you cannot guarantee that humans will follow it. Because it's difficult, some rules is difficult to follow. And the same is about models. You may introduce some directions in the prompt, but maybe model just don't understand how to follow it. If you, I believe that most of you worked with some AI system and you understand that some tasks, it follows your requests, but for some tasks it cannot. I don't know, just because it's difficult task. So we need to develop these patterns together with understanding what the model can do. Yeah, that's the issue.
Okay, thank you.
Mm-hmm.
Thank you. Another question. The risk, you mentioned the risk of skimming and misalignment. So I think the risk of skimming and misalignment are happening right now with Grok 4. Recently, I don't know if you have seen the trend on the social media about the some misbehaviors that been what do you call it, been presented by Grok 4, which is giving some anti-Semitic comments,
Yeah.
something about Hell Hitler, something like that. The recent trend in social media. So is the loss of control a present-day problem or a future problem? So, and if so, can we trust AI benchmark when they fail to capture these critical alignment failures?
Oh, that's a very good question. Can we trust AI benchmarks? No, definitely no. Currently, AI benchmarks is far behind AI abilities. So that's the issue, that the true abilities of closed source, for example, proprietary language models are far above those that reflected in benchmarks. So for example, in benchmarks you can compare the ability to solve mathematical tasks, right? But the model can also solve tasks about, I don't know, booking your journey, booking tickets and so on, buying you, collecting some shopping lists and reviewing papers, writing papers, and so on. It's very difficult to analyze, and there is no automatical scoring suitable for this. So that's why I believe that each industry has its own benchmarks. So currently, for my opinion, the main thing why we have no problems with it is because big models are developed by industries, and industries are responsible because they don't want to be sued for something. So they develop their own control benchmarks. For example, it's about chain of thoughts monitors. It's actually a very good practice, right? But when some user use LLM, it doesn't use such monitor, but OpenAI has it. So in this paper, it is describes the process, internal process of OpenAI, how they check that their model do not output harmful behavior, how they analyze the behaviors. And that's actually good internal practice. So here, I hope that we may trust the laws which suit industries for harmful behavior of their systems and the industries themselves. That's the only thing which I might tell here.
Thank you. One last question. So during your presentation, you mentioned some major AI risk, where you even highlighted loss of control in red.
Yeah.
So is a loss of control a is it a future problem or present day problem? I want to reference again the misbehavior presented by the latest version of Grok 4, presented by Elon Musk, like I think 2 weeks ago.
Yeah, I believe that it's the problem of close future. So it's, actually in the area of AI safety, if somebody reads these blog posts and these discussions, that the common argument is that this loss of control will happen suddenly. So it's not like you may just now, it's small loss of control, then it's larger, then more larger, and you will invent how to control the model. No, it's just there is no any problems, and at some point the model starts to achieve its own goal, which is completely contradictory to ours, and you just can't stop it. So it happens, and so that's why the authors of the report propose to think about it now. They consider it as actual problem for now, but now we cannot see cases of this, but we can see evidence that it may happen. So you know that actually in the world there is a lot of dangerous things. I don't know, like electricity can break and we all feel very badly, and that's the level of danger of AI systems also. So if somebody develop agent who has access to environment tools, to the internet, it could act as, I don't know, as computer viruses, for example. They are dangerous, but it could act as a very smart hacker, and we may have problems here. It might happen, yeah.
Okay, so one last question. So it's the Grok, I think, has been adopted by the American Pentagon, and it's if an AI model that has been even adopted by the American Pentagon can display some of these dangerous behaviors. So us as an upcoming academician and researchers, so what's your advice on for us and maybe next research direction we should take if an AI model that has been publicly adopted by Pentagon is displaying such kind of dangerous behaviors? So what's your advice directly to us?
That's a good question. We are not in Pentagon, actually. That's a good thing. My advice will be just to not, how to say, we need to be, that's very interesting things, it's behavior of current AI models, and what we can do is just use this and be responsible user and be attentive users. That's our own, the only function. We need to understand how it really works, not to watch on benchmarks. Yeah, so our benchmarks, sometimes we, as the researchers, we look for benchmarks and it looks that they reflect the situation. No, current situation, it's very different, and if you use AI models, you see that that's much more interesting things happen there. So just to watch by your own eyes, not only believe research papers like this.
Okay, so maybe as a researcher, if I want to take that as a, what do you call it, as a research direction, so do you think there is a promising future for me there?
I believe that it's very important research direction, and it will be more and more important. So the models become stronger, the safety departments should be in any companies. For now it's not the case, but it will be important direction. And from my point of view, the most interesting thing here is consider it as study in generalization, because it's very important. We have no theory, even theory, how LLMs are, how AI generalizes now, and practical things. That's for me more interesting, but that's also much more practical things for any business. Yeah, and it will be, I believe that it's promising investment in your future to study this direction.
Okay, thank you.
Thank you for the lecture.
Yeah, okay, thanks.